This is a video of several types of thermochemistry problems that you might encounter on tests. Here are the 3 learning objectives from the AP Chemistry LOs. We have something called the 0th law of thermodynamics. To illustrate, consider this piece of metal. I've got the atoms here shaking around to show that it's at a high temperature. What would be the energy change if it is put into the lower temperature liquid below? Well, intuitively we realize that the answer is that the fast vibrating particles on top, when they're put into contact with the molecules below, they will collide with those slower vibrating liquid particles. The faster ones will lose kinetic energy, the slower ones will gain kinetic energy. So the temperature of the metal will go down, the temperature of the liquid will go up. The 0th law, which was actually formulated after the 1st, 2nd, and 3rd law of thermodynamics because it underlies all of those laws, the 0th law says that substances with higher temperatures will transfer energy to those with lower temperatures when they come into contact. The 0th law says that it cannot happen that the kinetic energy in the lower temperature molecule would transfer energy to the higher kinetic energy substance. Now, in this kind of thought experiment, turn the video off and discuss what is the system and what are the surroundings. It may be obvious or not, but the system is the higher temperature metal, and then the surroundings would be the liquid that they are immersed into. Now let's go into a mixing identical liquids question. And here we have a 40-gram sample of water at 260 K mixed with a 50-gram sample of water at 330 K. We want to know the final temperature. And of course we have the same substance being mixed. And we give you the heat capacity, specific heat capacity of water. Now we know the absolute value of the heat lost by the hot water is equal to the absolute value of the heat gained by the cool water. And so we use the standard MCAT formula you see here, specific heat capacity times mass times temperature change. And so we plug in the numbers over here. Now, you could solve this because the two expressions are equal. You can see that on the left and on the right we have 4.184 joules per gram Kelvin. So we could just knock those out. In this solution we went ahead and multiplied the 4.184 by the 50 grams and the 40 grams to get 209 joules per Kelvin on the left with this expression, and 167 joules per Kelvin on the right with this expression. Notice on the left the final temperature appears after the initial temperature, which makes sense when you've got hot water cooling, and on the right the water is warming, and so the final temperature is higher than the 260 Kelvin. When we multiply both internal terms here, we'll do the distribution by the relevant coefficient. We get on the left what you see, 690 times 10 to the 4th, and on the right minus 4.35 times 10 to the 4th, combined with the temperature times their coefficients. We can then combine like terms and get 376 times the final temperature is equal to that number on the right. If we divide both sides by 376, we get the final temperature, which is 299 Kelvin. We ask the question, does this make sense? Well, we had more of the cool water than we had of the hot water. I'm sorry, we had more of the hot water than the cool water, and so it appears that we would have a temperature closer to the high temperature than to the low. And as you know, 299 is a lot closer to 330 than it is to 260. So the answer makes sense. How is temperature change related to the specific heat capacity of a substance. Specific heat capacity is Q over m delta T, if we solve the MCAT formula for C. So logically, as the heat absorbed goes up, that's in the numerator, the specific heat capacity will go up. Now, thus water, which is a high specific heat capacity, absorbs a lot of heat per gram. The next question we can ask is, as the specific heat capacity goes up, and if you keep the amount of heat put in and the mass the same, what happens to the change in temperature? Well, the change in temperature is in the denominator here, and so as this goes up, if we keep the amount of heat we use and the mass the same, the change in temperature goes down. So for instance, water has a much higher specific heat capacity than the ground does, and so water warms up more slowly than an adjacent piece of land. Given that, let's look at the temperature change near to and far away from bodies of water. Corpus Christi, Texas is right on the Gulf of Mexico. San Antonio is inland. Corpus Christi is actually closer to the equator than San Antonio. We would expect it to be hotter in the summer. However, if you look carefully, you see that Corpus Christi is warmer in the wintertime than San Antonio is because it's on the water. And in the summer, it is cooler than San Antonio because you have that heat sink, the water, large body of water, right close to the land. So even though it's more south than San Antonio, Corpus Christi is cooler in the summer. Now let's talk about energy and enthalpy with this interesting problem. We have a gas in a well-insulated 5-liter bulb, and we give the pressure and the temperature. And it's then connected by a closed valve to a similar bulb. And this has a vacuum in it. There is no pressure. What happens to internal energy, enthalpy, heat, or in the pressure volume product as the valve is opened? Well, I think you can realize, just begin thinking, that the pressure volume problem, pressure volume constant is going to stay the same. If you multiply the pressure by the volume, it's going to be the same if you don't change the temperature. The internal energy before and after, well, that ought to stay the same because the temperature is the same. Pressure volume product stays the same. Heat, it's well insulated, so we have not been able to transfer any heat in or out. Therefore, because of the definition of enthalpy, there is no change in enthalpy in this system when you open the valve. This is counterintuitive, but it is true. Now let's talk specific heat capacity, and we have this problem here with a 41.2 gram sample of metal, which we usually do this the same way. We heat it up in boiling water and then put it in a calorimeter, and we see the final temperature, so we know the temperature change of the water in the calorimeter and the temperature change of the metal. In these problems, we tend to assume that there's been no heat lost to anything except the water and the calorimeter. That's not exactly true, but it's good for calculation purposes. The heat lost by the metal is equal to the heat gained by the water, and so we use the MCAT formula on both sides. When we then solve for the specific heat capacity of the metal, C metal, we get the MCAT for the water divided by the temperature change and mass of the metal. When we plug the numbers in, as you see here, you get 0.37 joules per gram Kelvin. That's the way you do these specific heat problems. Question: what instrument is used to measure directly the enthalpy change in a chemical reaction? Turn the video off and discuss this, and then come back for the answer. The answer is there is no such instrument, because, as you know, the heat is measured by temperature change and mass of the substance. So you really have no such thing in terms of a direct instrument. But a calorimeter enables you to measure both the mass and the change in temperature. Frequently you will see something called work calculations, and let's determine the work associated with the expansion of a gas from 12 liters to 70 liters with a constant pressure of 10 atmospheres. And we know from the definition that the work is minus P delta V. Expansions involve a positive change in volume, and so we subtract the 12 from the 70, multiply by the 10 and the negative, and we get negative 580 liter atmospheres. There are two significant digits here. This is a diagram of the change of the expansion, and just to justify this, normally to make an expansion like this happen, just doesn't happen by itself. You have to add energy either by heating the gas, say with blowtorch or something from the outside. You heat this gas and it expands, or by an explosion. Now, that is a negative change in energy which shows up as the expansion, and that's justifying the fact that this is a negative work. Now, bond energies and enthalpy of reactions. You may remember from an earlier semester that we have to break bonds. That takes energy, and then we make new bonds in the chemical reaction. So this reaction of ammonia gas with chlorine gas to produce nitrogen trichloride gas and hydrogen chloride gas, we see only single bonds are involved. How do we find the delta H of this chemical reaction? Well, we break bonds and then we make bonds. Calculating bond energies, breaking bonds is endothermic, making them is exothermic. So we start off by 3 of the nitrogen-hydrogen bonds we're going to break, and then 3 of the chlorine-chlorine bonds that we're going to break. We subtract the energy we get out, and with the 3 nitrogen-chlorine bonds and the 3 hydrogen-chlorine bonds. When we do this mathematics, we end up with 9 kilojoules per mole. This is reactants minus products, which is very different from most thermodynamic calculations. Now you can standardize a calorimeter so we can find out how much heat is involved when there's 1 degree change in the whole calorimeter. And we use benzoic acid typically in a combustion to do this. Here we get mass, temperature change, and the delta H of the mole of benzoic acid. Well, we need to know how many moles we've got. We divide by the molar mass and we get 0.0205 moles. Let's go to the next slide. Now, how do we figure out what the C of the whole calorimeter is? Well, we have less than a mole, so we're going to multiply that number of moles by the kilojoules per mole, then divide by the temperature change that we see in the calorimeter. So the calorimeter has a C of 12.7 kilojoules per degree. And enthalpy of combustion of fuel, if you have a calorimeter with that kind of C, and you burn a fuel with a molar mass that you see here, and get the temperature rise, we can calculate the enthalpy of combustion of the fuel in this way, 305. And that, of course, is going to be a negative number. Finally, endothermic, exothermic. We want to show a thermochemical diagram for the condensation of ethanol. We get delta H of vaporization, but we're going the other direction. We're going vapor to liquid. And if we've got 3 moles, we're involving 116 kilojoules. And here is, it's of course negative, it's exothermic. And there's the diagram that you're supposed to make. Here is the before, and here is the after, and that is the way we do these things.